Greetings to all. This is Ranjini working as an assistant professor in the Department of Computer Science and Engineering at RMD Engineering College. In this lecture, let's see about AVL tree. AVL tree is a height balanced binary search tree. As like binary search tree, in binary search tree, how do we insert an element? We will compare each element with a root element. If the element is lesser, means we will insert at the left side, and it is greater, means we will insert at the right side. As like that, AVL tree is also we will do the same type of insertion. But what we will do is after inserting each element, we will check for the balance factor of all the nodes available in a tree, and the balance factor should be 0, 1 or -1. If it arrives as 2 or -2 occurs, means we have to do some rotation and we have to make the balance factor to 0, 1 or -1. So how to calculate the balance factor? As balance factor will be equal to the height of left subtree minus height of right subtree. Now, how to represent a node in a binary radial tree? In binary search tree, how the node will be? The only 3 elements will be there in a node. That are a data and the address of the left child and the address of the right child. But here there is one more element is added, which means the height of the node, which means height means the balance factor. The data, address of the left child, address of the right child, and one more element, which is the balance factor. Also, we have to save in the each node. So, if you are saving the balance factor, means this will be our node representation is int data. So, int height is also an int, which means 0, 1 or -1, or max it will get 2 or -2. At that moment, we'll make a rotation and we will make it to 0, 1 or -1. So, this is also the integer value. And left and right holds the address. So, address node star left child, struct node star right. So which means address. Since it's the address, we are representing here as the struct node. So why do we use the AVL tree? So AVL tree controls the height of the binary search tree by not letting it to be skewed. Which means, suppose imagine what is the time complexity of the binary search tree? Obviously, order of log n in the average case. But the worst case, it is order of n. Which means if the completely if it is skewed means I hope we know all the elements are arranged in one side. We are inserting all the elements at the left side, which means all the elements are facing towards the one side. We call it as a skewed. So in this particular statement, it becomes a worst case. So insertion, deletion, traversal means everything that happens at the order of n times. But AVL tree, we are making it to be unskewed, which means we are balancing. If we are balancing a tree, means it will become, obviously it will not be a skewed tree. So the complexity becomes order of log n. Suppose if you want to insert an element, if I'm inserting a element means smallest element, means obviously I'll search for only the left side. The greater element means I'll search for only one side. So here that happens is order of the complexity becomes order of log n. So that is the reason why we are reducing the time complexity which occurs in the binary search tree. So what are the operations we perform in AVL tree are insertion, deletion and traversal. Traversal means reaching all the nodes. Now let's see it. Look at the AVL tree rotation. There are 4 types of rotation. It is left rotation, right rotation, left rotation, and right left rotation. Inserted node is at the left subtree of the left subtree of it, which means if we are inserting a node, our left rotation means the node which we are inserted will be at the left side. Left side means what? Now look at this picture. If you look at the picture, it will be more clear for us. Now let's look at the right rotation. So right rotation, which means how we are performing a right rotation. So our node will be at, this is our root node. Our inserted node is at the right subtree of its right child. So right child's right child. Now this is the right rotation. So A is our root and its child is at right side, and again we are inserting the child of B at its right side. So which means insertion node is at the right subtree of A. Now, how to perform a rotation is, now let's see the implementation part of the right rotation. Suppose imagine this is our node. So now look at the balance factor. Here the height of balance factor is height of left subtree minus height of right subtree. So here how to calculate a balance factor? Height of left subtree is 0 and right subtree is also 0. 0 minus 0, which is 0. So here the balance factor will be the height of left subtree is 0 height of left subtree is 0 and right subtree is 1. So 0 minus 1, here it will be minus 1. Okay, here it's represented as 1, but here exactly it comes as minus 1. Now here also the balance factor will be minus 2. Left subtree 0 minus 2, which is minus 2. Now how to perform a rotation is, since every node is facing towards the right, we have to make a left rotation. So how to perform a left rotation? So RR rotation means moving a node towards its left. So we are making a B here, and a B we have to make a B as our root, and A will become our child. So one single left rotation, A has to be rotated to come towards the left side of B. Now how to perform a implementation part of the left rotation? Let's look into the implementation part of the left rotation. Look at this step, it will be more clear then for us. Now this is our node representation, how our node will be. So how our node will be, this is A is our node. Imagine A is our node, and this is the null value. Since it does not have any right child, so left side value is null and right side value is 200. Address of right side is 200, and obviously I told you one more data we have to be add, that is its balance factor. Here its balance factor will be minus 2. And sorry, here everything will be minus 2, minus 1. I have represented wrong. So here it will be minus 2. Now how to do a left rotation is, initially node rotate left of node star y. So I have considered the root node. The root node is now y is pointing towards the root node. So root node address, suppose the root node is 100, means I am saving 100 into this particular position. Now what is my aim? I have to perform left rotation, which means this B, in this B's left child should be A, isn't it? If I want to make B's left side to be A, first I have to name B. I know only the root node, so I have to give name for this particular node. So how I am giving is Y's right child. So B is Y's right child, isn't it? Y's right child is equal to X, which means I am making X to point to this location. So X memory address is pointing to this. So if the address is 200, so X holds 200 now. Now, what is the next step is? Next step is I have to perform a rotation, which means I have to make the Y to, I want to make Y to point towards its left. X should become the root. Now, how to perform that? So, where should I have to place Y is? I have to place, instead of this null, I have to replace this null with 100, isn't it? So, here how to replace it? So, X left is equal to Y, which means the Y's address I'm going to place at the X left. So this position becomes null. Now this, look at this part. This is how my second, after doing the rotation, this will be my step. So obviously now I have made this X to point to move towards its left, but look at this arrow. I have just given a connection now. Connection to Y. Y's left is now, the left child is X now, but I haven't I haven't disconnected this link, isn't it? So my next step, next process is to disconnect this link. So if I want to disconnect this link, means what should I have to do? I have to replace this particular position with null. So what is the name of this position? Is X right. Sorry, this is Y, isn't it? It is Y. So Y right should become, this is Y. The name of this node is Y, isn't it? 8th node is Y. So Y right should become null. So I am placing Y right is equal to null there. Now look at the LL rotation. LL rotation means we are inserting all the node is facing towards the left. Since all the node is facing towards the left, we have become, the tree has become imbalanced. Now how to perform the rotation is obviously node star Y. So what does it mean? This node name is Y. This node, name of this node is Y, which means the pointer variable. Y is a pointer variable which was pointing towards this address. Suppose if memory location is 100, means Y holds 100. Now what is the next step is I have to give name for this location. Since I know only Y, I have to give name for this memory location. So how to name this? Where it was at Y or the left. Y's left is equal to, means X is equal to Y's left, which means Y's left address I'm going to save it X. So X is now X points to this location. Then what is the next thing? If you are making left rotation, means I have to make shift one this side. So C has to come left side of right side of the B. So how to perform this? So BX right. This name of this is X, isn't it? So X right is equal to what? This is Y. X right is equal to Y. Now I have made this to move towards the right. Next step is I have to cut this link. If I want to cut this link means what should I have to perform? It is the name of this node is Y. So Y left will be equal to null. This is how to perform LL rotation. Now let's perform LR rotation, which means this is a double rotation. Previous two rotation we call it as a single rotation, and this rotation is the double rotation. So how to perform double rotation is when we have to perform double rotation is if our node is in the zigzag format, as like this format. So if this is our case, means when to perform a double rotation, first we have to make this node move towards its first we have to make a look at the node. First we have to make a node to look like this format, and towards look like a LR format or RR format. So here what we are doing, every node is for first we are making this node. Since see how to identify the rotation is, since look at the node, our node is placed at the right side of it. So since it's placing at the right side, first we have to make a left rotation. So if we make a left rotation means it will be in this format. Then we have to perform one right rotation. So LR rotation. First we have to make a left rotation, which means 12 will come on the top, 11 will come here, and then we have to make a left rotation. And the next rotation is RL rotation. RL rotation means first what we have to do, we have to first perform a right rotation, and then we have to perform a left rotation. So look here, first I am performing one right rotation, which means 13 comes to the top and 15 comes to next to 13, and then we are performing one left rotation. That's all about the AVL tree rotations, and let's see the implementation part in the next video. Thank you for watching the